my forces homework, notebook problems, they should look something like this-ish, assigned last time. And I'm going to go through my answers, and I'll again also upload a PDF. So those problems are from the physics classroom, two somewhat different problem sets. So the first one was PC1, or problem 1. You had a 6,000 kilogram elephant. The question is, what's its weight on the Earth? What's its weight on the Moon? So weight is just m times g. So 6,000 times 9.8 kilograms times 9.8 newtons per kilogram, 58,800 newtons on Earth. So not all objects have the same force on Earth. They have the same gravitational field strength, which is around 9.8 or 10 newtons per kilogram. And I noted up here, I'm using 9.8 newtons per kilogram, but you certainly can use 10. Just make sure you show me in your work. So for the second one, on the Moon, it says gravity's field strength is 1/6 as strong. And so I just take 6,000 times 9.8 times 1/6. I guess I could have divided things, but 9,800 newtons. I didn't want to use only 1,000 kilograms of mass, because mass is the same everywhere in the universe. It's really the gravitational field strength is 1/6 as much. And a little sneaky thing here, newtons per kilogram and meters per second actually mean the same thing. And if you want, I could derive that at some point. For problem 6, it's asking for the essentially force acting on a person who is accelerating at 450 meters per second. He and his ship each had 82 kilograms of mass, which is weird. So I get the total mass multiplied by the acceleration. So that force is around 73,800 newtons. For problem 14, this is fun because it's Dominic and his sister. And so he is trying to pull her in a wagon. So the net force is the difference of the horizontal forces. That's 28 newtons. The mass I would get by taking this weight, 304 newtons, which was given, dividing by 9.8. So the mass is 31 kilograms, which is ridiculously small. That's somewhere around 65 pounds. I doubt that she's only 65 pounds, but whatever. The acceleration is simply net force over mass. That's Newton's second law. And so that would be whatever you get for part A divided by whatever you get for part B. So it's 0.9 meters per second squared. Problem 17 deals with air resistance and asking about the acceleration when there is air resistance. So in this case, I'm splitting up this net force variable into the two forces that are causing it. Gravity acting down, drag acting against that. So drag is like friction over the mass of the system. So acceleration is mg minus 118 newtons over mass. And, oh, that's weird. Oh yeah, m is 82.5 kilograms multiplied by 9.8. That gets me the gravitational force of the person minus 118 newtons of drag force. And then the mass is 82.5. So I have a net force of 690.5, mass of 82.5. That's an acceleration of around 8.4 meters per second. Over time, as the skydiver moves faster, the drag force will increase, but the gravitational force will stay the same. So the net force and acceleration will decrease. Okay. Next one is number 21. And for number 21, it's a rocket, and it was basically accelerating upward at 45.9 meters per second. Determine the upward thrust. So you need to be careful. You can't just multiply 0.104 times 45.9, because this acceleration is caused by a net force, and that net force is the thrust subtracting off the force of gravity. So I know the net force is 4.77 newtons, but if I look at this free body diagram, which I suggested that you draw, net force is equal to thrust minus force of gravity. So 4.77 is equal to T, which I'll call the thrust, minus M, which is 0.104 kilograms, times 9.8 newtons per kilogram. So that means the thrust has to be bigger than the net force. The thrust is 5.79 newtons. For number 26, this deals with something that's a coefficient of friction. We will learn in class, probably today, the coefficient of friction for a moving object is equal to the force of friction on the object divided by the normal force, which is the perpendicular component of force. And for a flat surface, this normal force would equal the gravitational force. So you were given that the object had 84 kilograms, accelerating at right at 1.2 meters per second squared, coefficient of friction was given, and the question is how much force am I pushing with? So the first thing I'm going to do is figure out the weight, 823 newtons, that's m times g. So the normal force is 823 newtons. Coefficient of friction times the normal force is equal to the frictional force. So that's 0.35 times 823. So that's 288 newtons. So now, if I go back to this, acceleration is net force over mass. That's my pushing force minus force of friction over mass. So I can rearrange that and get force of push minus force of friction equals mass times acceleration. That's what I did here. That's what I did here. So this will come out somewhere around like close to 100. So it's basically, I think it was 101 or something like that. Force push minus 288 equals 101. So the push is 389 newtons. Again, this was not assigned for you this time. Problem 2, this is just simply a vector problem, looking at the horizontal and vertical components. So hopefully that's very straightforward at this point. For problem 2, also a vector problem. Notice I'm trying to give you a couple of these before we have our test, which will be both over vectors and forces. It's a pack of 3 Arctic wolves fighting. So you want to determine the net force. So in this case, I'm making a T-chart. We've got these 3 forces. I chose north and east as my directions. So I have 424 and 424 when I split this one up in 2 components. Negative 500 because that's down. Negative 250 because that's to the west. So I end up with a negative 76 newtons to the north, 174 newtons to the east. So my resultant force is 190 using Pythagorean theorem. Notice I drew that out. The angle of that resultant force, I used inverse tangent of 76 over 174, so that's around 24 degrees. So the resultant force is 190 newtons at 24 degrees south of east, or 66 degrees east of south. The acceleration is simply now that net force over mass. So same direction, you probably don't really need to say that, but 190 newtons of net force divided by 750 kilograms of mass of the polar bear. And so it's 0.25 meters per second squared. Problem 13. This is a symmetrical problem. So essentially, since the angles are the same, tension 1 is equal to tension 2. So rather than having 2 separate variables, T1 and T2, I'm just saying that's equal to T, which is the tension. So big idea here is force up equals force down. So the weight caused by this, the mass of the sign, is going to equal the vertical components of tension upward. So first I'm going to get the weight of the sign. That's m times g, 43.1 times 9.8. It's 422 newtons. And now I'm going to look at the vertical component of this. And I only drew one. I don't need to draw both. But if this is 34.5 degrees from horizontal, I'm trying to find this vertical component that's opposite. So essentially I have t sine of 34.5 degrees is the vertical component of this one, and also t sine of 34.5 degrees is the vertical component of that one. So because I have 2 of those, 2t times the sine of 34.5 degrees is equal to the force down, which is 422.4 newtons. So I end up doing the trig. Sine of 34.5 is 0.566. Multiply that by 2, I get 1.13t is equal to 422 newtons. And therefore the tension in each rope is 373 newtons. So this is very similar to an example I did in class. Problem 9, I also noted that you did not need to do because it had a coefficient of friction in it. But this is a more complicated case. The upward component, or the normal force, will not be the same as gravity because this is pulling up at an angle. And essentially you're being asked here to find the acceleration. If you're pulling with 692 newtons at 36 degrees, you got a coefficient of friction of 0.548, you got a mass of 112 kilograms. So taking this, the horizontal component of force is 560 newtons, the vertical component of force is 407 newtons, and therefore those I'm going to take into account. The gravitational force down is mg, so that's 1,098 newtons. The big idea is the vertical forces have to balance, so that's let us going to find the normal force. So force up equals force down. The normal component of force plus the vertical component of the pull, actually it's the normal force plus the vertical component, is equal to gravity. So force up equals force down. So we've got F normal plus 407 newtons equals 1,098 newtons. That lets me know that this is only 691 newtons. Now I'm going to use the coefficient of friction and the normal force to find the force of friction. Again, this is the formula we're going to develop. So force of friction equals coefficient of friction times the normal force. I know the coefficient I was given. The normal force I just figured out. So the force of friction is 378 newtons. So finally, to get acceleration, I'm going back to that master equation. Newton's second law is net force over total mass. My horizontal pull was 560 newtons. The frictional force is 378 newtons. They're acting different directions, so I subtract them. And then I divide all that by the mass, and that's the acceleration. So that is a lot of problem. Say that's why I didn't want to assign it for this time. Anyhow, I hope those help, and we'll be ready for our test on Tuesday.